in this direction, you turn it in clockwise direction. Okay, so first it will induce voltage in winding A, then C, then B. So ACB, ACB, ACB. That is the negative sequence. Or you can represent here, you have a vector A, you have a vector C, vector B. It is turning in this direction. So first you will see A, after that C will come, after that B will come. So this is what is actually the negative sequence, ACB, ACB, ACB. So each voltage VA, VB, VC, it is made of zero sequence component, positive sequence, and the negative sequence. Now, if you see here the same thing, so this is positive, we are talking about positive sequence, ABC, ABC, ABC. So positive sequence, we use A1 here. Okay, see 1, VA1, VB1, VC1. And for the negative sequence, ACB, 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 we use 2 here. VC2, VB2, VA2. So if you see the relation between VC1 and VA1, it is shifted by 120 degree and unit vector. So this is what the A factor we use. A is 120 degree rotation. If we say A square, 120 plus 120, 240 degree, and A3 will come. So if you see this is equal to 1, then you give 120 degree shift, it is A. If you give 240 degree shift, it is A square. And if you put another 120 degree, it will become A cube, which is equal to 1. So what for positive sequence, suppose we say VA1 is equal to V1, then VB1 is equal to this, because we have seen VB, to get the VB1 in VA1, you have to multiply it by A and another A. So that is why we have A square VA1. Similarly, VC1, if you see the relation between VA1 and VC1, in VA1 you have to multiply only one A, which will give 120 degree rotation. So that's how it has come like this. VA1, if we say V1, VB1, A square VA1, VC1, A VA1. Okay, to simplify you can write this. Now for negative sequence, VA2 equal to V2. Suppose VA2 we write V2. So if we have to get VB2, then we have to multiply it by single A, which will give 120 degree phase shift. And VC2, so this is 1A and this is another way, A square. So A square VA2, this is VA2, if you multiply it by A square, it will give 240 degree shift. So that is VC2. So this way you can write these equation VC2, A square, VC2. Now the zero sequence component, they don't have the phase shift. See, they are in the same phase, same amplitude. Okay, and they are rotating with the same frequency. So VA0, VB0, VC0, they are of the same amplitude. Okay. So now if we write these equations which we have seen earlier, see VA1 equal to this one. So you can write these equations using the original equations by putting the value of VB1, VC1, VB2, VC2, like those things. So this is, now if you have to calculate V0, you just take the sum of this. So if you see this V1 plus A square V1 plus A V1, V1 is common, so it will give you 1 plus A square, which is equal to 0. They are 120 degree shift apart, right? This way. Sum of these is 0. So this will all become 0. So V0 will become VA plus VB plus VC divided by 3, because 3V0 here. Now if you have to calculate V1, so here in this equation you can multiply it by 1. In this equation, to get V1 you have to multiply it by A, because then it will become A cube. A cube is equal to 1. Here you see it is A here, so you multiply it by A square here. So that way you can eliminate other things and V1 you can calculate. Here to calculate V2, you multiply it by 1. Here it is A, so you have to multiply it by A square in the whole equation. In the whole equation, here A square you multiply it by A, so that other terms will become 0 and you can get the V2. Same equations are for the currents. So this is how you can write V1 equal to this, V2 is equal to this, V0, and same type of equation for the currents. Now if you have a balanced three-phase source, so these are the equation you can write, right? Balanced three-phase source, same amplitude, 120 degree apart, VB equal to A square VA, VC equal to AV. So if you calculate V0, so VB you will be putting here, VA, AVA you will be putting VC here. So what will happen? You see, you take VA out and then you will have 1 plus A square, which is equal to 0. So finally you can say V0 equal to 0. Okay, so if you have three-phase balanced system, zero sequence component is 0. What about V1? So this is the equation for V1. We already know. You put the values there, like VB equal to A square VA, right? And VC is equal to AVA, so it become A cube. This is also A cube. So finally V1 become AVA. Similarly for V2 you can verify that negative sequence component is 0 if you have three-phase balanced system. So a balanced three-phase source is equivalent to a positive sequence source only, with negative sequence and zero sequence sources being 0. So how you are representing three-phase balanced source? This is the positive sequence, this is the negative sequence which is 0, and this is the zero sequence which is 0. Now if you have a non-sinusoidal unbalanced system, so same equations, you see, IA, we have already seen this equation for I. Similarly, we have equation for IB also, like I0 plus A square I1 plus A I2, the same equation which has been used. Only thing we have done, we have put the harmonics, fundamental, second, third, fourth, all the harmonics. So this is basically sum of all the harmonics. Okay, so this is how we can represent IA current in phase A, which includes all the harmonics. So you can represent it because the currents are unbalanced. Same way, IB you can represent by this, and IC you can represent by this. Now you can find zero sequence current of nth harmonic. This is the same equation we have seen. I0 is equal to IA plus IB plus IC divided by 3. This is what we saw. This is the same equation. Only thing is that we have put the harmonic here. If it is fundamental or third or fifth, those harmonics. So total sum of all the zero sequence currents you can represent for all the harmonics. Sum of zero sequence currents of all the harmonics you can represent by this. Similarly, sum of positive sequence currents of all the harmonics. Sum of all the negative sequence currents of all the harmonics. So this is how you can write. Now I will give you a very simple example. See this example. Here you have to consider a non-linear load introducing the following harmonic current of rank 5, fifth harmonic. Okay, so you have the fifth harmonic and you have to find the sequence of the fifth harmonic. Okay, whether zero sequence current, is it the zero sequence or it is a positive sequence or it is a negative sequence. So you can put the same equation which we have already seen. Okay, so fifth harmonic, so you can write it this way. So because frequency is 5 times, you can write it this way. Now the fifth harmonic for the phase B, this is for phase A, phase B, it is minus 120. The fifth harmonic is there. Why it is minus 240? Because you can say 3 plus 2 multiplied by 120 degree, right? 5 you can write 3 plus 2. So 3 multiplied by 120, it will be 360 degree, which is 0 degree. So it remains only 2 multiplied by 120, so it will give you minus 240. Similarly here, 5 multiplied by 120 and finally plus 240 degree. So you put these values here. These values here. And see what is the value of fifth harmonic, zero sequence of fifth harmonic. Why it is 0? Because IA5, this value, IB5 is minus 240 or this may be plus 120. Right? Minus 240 or plus 120 is same, right? And plus 240, that will be minus 120, right? If you see the full cycle, 360 degree, so this will be minus 120. So basically, IA5 with 0 degree, IB5 with plus 120 and IC5 is minus 120. So sum will be 0, right? Because they are balanced. Same way, you can calculate I15. So IA5 is this value 0. IB5 is this and A is there Okay, minus 240 plus 120. So that will be minus 120. And here you have a square for IC5. A square means plus 240. A square is plus 240. Plus 240 and another plus 240. So plus 120. This will be plus 120. Is it clear? You just have to put A. A is what? A is 120, right? A square is 240. A cube is 1, right? We already know. So put these values there and you will see that I15 is 0. Now you calculate this negative sequence with this equation. Okay, let us check it. IA5 is this one, I0 degree, right? So this is I0 degree. A square is plus 240 and this is minus 240 plus 240 minus 240 again 0 degree, right? So I0 degree. Now here A is plus 120 and here you have plus 240, 360 degree, it means 0 degree. Is it clear? So you have to see the phase shifting with A, and finally you will see the negative sequence of the fifth harmonic has the value A. It means fifth harmonic is a negative sequence current. So this is how mathematically you can see if the fifth harmonic is positive sequence, zero sequence or negative sequence. If fifth harmonic is balanced, this is the condition. If fifth harmonic is balanced, then only it has a particular sequence. If fifth harmonic is unbalanced, then it will have zero sequence also, it will have negative sequence, it will have positive sequence. But here we are talking about balanced fifth harmonic. If the fifth harmonic is balanced, it has the negative sequence. Same way, you can check for seventh harmonic. You see? So yesterday night I was doing this thing. For seventh harmonic, you can write this equation and 7 multiplied by 120, 6 multiplied by 120 will come out to 0. So it will remain minus 120. So you have minus 120. Okay. Same way 7 multiplied by 120. So 6 multiplied by 120 which will come out 0 degree. So you will have plus 120 degree. Although this is a different thing, that now what you can do, you can be smart. You can just draw this diagram. Okay, this is IA 7 and this is IB7 and this is IC7 plus 120 minus 120, right? And vector is rotating in this direction. So you can say A, B, C, A, B, C. So you can say, okay, this is a positive sequence. But mathematically, if you have to check mathematically, see, I07 equal to this value, put all those values here and you will see the sum will be 0. Same way I17, you can check, this is the equation for positive sequence. Put the values of A, plus 120, plus 240 here and then put IB5, IB7, IC7 here and you will see that this is the value. And then I27, second harmonic, this negative sequence of seventh harmonic is 0. So mathematically you can see the seventh harmonic, if balanced, seventh harmonic if balanced is a positive sequence. So this is how mathematically you can see the fifth harmonic is a negative sequence if balanced. If seventh harmonic is unbalanced, then it will have zero sequence also, positive sequence also, a negative sequence. So this is a very important thing to verify. And finally, what you can do, you can make a table. Sequence of the harmonic, harmonic order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is how you can write the table, and you can see which harmonic is positive sequence, which harmonic is negative sequence. Okay, so now you will say, oh, this is long table. If I want to see the 25th harmonic, do I have to make a table until 25th harmonic? That is not necessary. You just see the equation. For positive, this is the equation. H equal to 3k plus 1. For negative sequence, H equal to 3k minus 1. And for zero sequence, H is equal to 3k. So these equations you can use. Okay, now tell me, if I have 25th harmonic, 25th harmonic, is it a positive sequence or zero sequence or negative sequence? What will be the 25th harmonic? You should be able to tell just right now. It should not be, because you know the equation here. H is equal to 3k plus 1. If k is equal to 8, 3 multiplied by 8 is 24 plus 1. So it will give you 25. It means 25th harmonic is a positive sequence. So you don't have to do all those calculations. That is just to verify mathematically if you are right or not. So this is very important to find. Before you do the harmonic cancellation, you have to know if certain harmonic is a positive sequence or negative sequence. Zero sequence you will know anyway, multiplied by 3 it will be easier. Okay, tell me 29th harmonic. 29th harmonic, what is the sequence? If 29th harmonic is a balanced harmonic, what will be the sequence? Negative. See, so fast you can tell. It's very easy thing. You just have to know the trick, right? Okay, 35th harmonic. 35th harmonic is what? 35th harmonic is negative. Okay, 3 multiplied by 12, 36 minus 1, then only you will get 35, right? So 35th harmonic is a negative sequence, and 37th harmonic will be the positive sequence. See, it is so easy. And now, so we will use this thing later. Now you know the triplet harmonics. Triplet harmonics means multiple of 3. So they may be present in 3-phase 4-wire system. They may be present if single-phase rectifier on 3-phase circuit is there, or you have single-phase induction motor on 3-phase system. Mostly, and there are many other cases, you may have triplet harmonic. So suppose the phase A current is like this. This is phase A current. You can find the fundamental component, and there is a third harmonic. In 1/2 cycle of fundamental, you have 3/2 cycle, so it is a third harmonic. So this is phase B now. So here again you will see the fundamental, and then you will see the third harmonic. Now for IC, phase C current, and similarly you can find the third harmonic. although the original current IA, IB, IC, see here you have 120 degree phase shift. See, from here to here 120 degree phase shift here you have. But the third harmonic of phase A, third harmonic of phase B, and third harmonic of phase C, they are in the same phase, same amplitude. So when they come to neutral, if current IA, IB, IC are balanced 120 degree apart, the sum will be 0. But if their third harmonic are coming to the neutral, they are same magnitude but in the same phase also. So that why you will have the sum of IA3, IB3, IC3, you will have sum of these, and in the neutral you may have very high current. So the engineer in a plant should be very careful what kind of load you are having, what kinds of harmonics are being generated. If there are zero sequence harmonic which may flow in the neutral wire, and sometimes they overload the neutral wire and they may heat up, and in very worst cases they may burn also the neutral. So this is very important about the triplen harmonic. Many times we will see that here you have non-linear load which is generating third harmonic. So third harmonic is trapped in delta, so they will not come out here and they will not pollute the network if you have a delta here. Okay, that we will see soon. Now we will hurriedly see this three-phase transformers. Okay, three-phase transformers, sorry. In this we will see, because in India as well as in North America there are so many different kinds of three-phase transformers are used depending on the application and requirement. Okay, so you have DY1, so we will hurriedly see DY11, DY1, YD1, YD11, DZ0, DZ10, and then we will see harmonic elimination by phase multiplication. So see, if you have this three-phase transformer, if we say DY1, what does it mean? D, capital D. It means on the primary side, it is delta connection. Y is small in small letters. It means small letters means the secondary side. So secondary side is star connection or Y connection. Now what does it mean 11? 11 specifies the phase shift it will give, right? So you see this diagram, I have already drawn this diagram, and this is the clock. So 12, 3, 6, 9, those are there. Okay, and if we say 11, so see there are 12, 360 divided by 12, it means every hour is representing 30 degree, right? So 30 degree represents 1 hour. So if we say 11, this is the reference, okay, and this is, if we say this is on primary side, on the secondary side we have 11. It means secondary side voltage is leading by 30 degree. So if you use this transformer, on secondary side it will give 30 degree leading. If you say DY1, again the primary side you have delta winding, secondary side you have star winding. 1 means here. It means secondary voltage is lagging by 30 degree with respect to the primary. So if we say YD1 transformer, primary is star, secondary is delta, and the secondary voltage is lagging by 30 degree. One is the lagging here, right? This is the reference, this is the one. YD11 30 degree leading. Then you may have YZ1, that is primary is star connected, secondary is zigzag, and then 1 degree 30 degree lagging. DZ0. So these things are there. So giving you the basic idea, suppose this transformer is delta star connection, DY11 here. So you have 3-phase transformer, or you can use 3 single-phase transformers. Technically there is no difference. If you use 1 3-phase transformer or 3 single-phase transformer, technically there is no difference. Only difference is you have 1 box of 3-phase transformer. Sometime that transformer 300 MVA, 400, 500 MVA, there is one company ABB, Asia Brown Boveri, but now it has been purchased by Hitachi Energy. So we have a big plant there in Montreal. So they make big transformers. Sometimes the transformer is as high, even higher than this room, and maybe almost cover this room, maybe more than half of this room size. So they make such a big transformer, 3-phase transformer. And if you have this kind of transformer, it is very difficult to transport this transformer. You need special means to transport that transformer. So this is a big advantage. Although the efficiency is high of single 3-phase transformer, has higher efficiency than 3 single-phase. 1 3-phase transformer, big box, but 3 single-phase transformer, small box, their efficiency is little bit lower than 1 3-phase transformer. And then what if you want an emergency transformer? If you have a 1 big 3-phase transformer, does it mean you need another such 3-phase big transformer which will cost a lot? But if you have 3 single-phase transformer, then you need another small single-phase transformer to replace if there is some repair. Moreover, it is easy to repair single-phase transformer. It is very difficult to repair 3-phase transformer. So these are some advantages and disadvantages of 3-phase transformer or single-phase transformer, right? Sometimes what we do, okay, there is a community and which has some houses, and suppose it has it needs requirement of say 60 megawatt of power, so you need transformer. But then you see then in future more residences will be added, so you may have more requirement. Perhaps instead of 30 you may need 90 MVA transformer. So what you can do, initially you don't want to invest on 3-phase transformer for 90 MVA. It will be very costly investment in the beginning. So you can start with only 2 single-phase transformer, and you can have, instead of having delta connection, you can have VV connections, and which will give you 58% of efficiency. So this is what, and then after few years you can buy the 3rd transformer. So this is how you can delay the capital you are investing. So this is in parallel of this. This may be 1 single phase transformer. This is parallel with this. This is another single phase transformer. This is in parallel with this. This is another single phase transformer. So this is how you may connect. So if you are looking for single phase transformer, this is the relation V1 by V2 is equal to N1 by N2, you already know. And V1 on primary side we use capital letters. On the secondary side we use small letters. So you see, you can write this relation, and then VAB equal to this. If you see this phasor diagram, this is VAN, VBN, and then VCN. So to calculate VAB, you take minus VBN and then sum of VAN and minus VBN, it will give you VAB. So basically VAB is leading 30 degree with respect to VAN. So this is what we have written. This is VAB, this is VAN plus 30 degree, and you simplify, you put this value here. So finally it will give you, M is the transformation ratio, right? And divided, if you say capital M is equal to M by root 3. So this is the global group transformation ratio. So you can write this. And the primary, we know already in single phase transformer, N1 I1 is equal to N2 I2. Okay, so this is how on the primary side I1, see IAB is flowing in this direction in the primary. Okay, so this is IAB current in this winding and IA current in the secondary, IA current here. So finally, using this equation, you can write, similarly you can write for this, similarly you can write for ICA. All these are the current in the primary of the single phase transformers. Now IA is equal to, this is the anti-current, sorry, it is taking long time to describe. IA is the primary line current, which will be equal to IAB is going in this minus ICA. Okay, so IA is equal to IAB minus ICA. Now you put the IAB value, ICA value, and finally you can find for a balanced system, you can write this equation, and that you can see in this diagram also. IA is here, this is IC minus IC, sum of this, it will give you IA minus M, IA multiplied by M. So this is what we are writing. Okay, but for balanced system, zero sequence currents are zero. Okay, now if you have an unbalanced system, you can write IA equal to this, the same symmetrical components. Okay, and then you can write IC1, IC2 equal to this, IC0 equal to, because IA0 equal to IB0 equal to IC0. Then you can simplify negative value, and then here you can see 1 is here, and A, if you subtract IA minus IC, so I1 minus A, IA1, and 1 minus A square. So you can calculate here, this is A square minus A square, sum of 1 and minus A square, 1 minus A square, which will give you plus 30 degree shift. And 1 minus A, this will give you 1 minus A, this is minus 30 degree phase shift. Okay, so what you can see, IAB is the current, this is the equation we have seen in single phase transformer, and IA, if it is distorted, it has IA1, I2, IA0. So zero sequence current is present. So if we say IAB, here you see zero sequence currents are present, IA0, IB0, IC0. But if you calculate IA using this equation, okay, zero sequence currents are absent here. It means in this transformer, if you have a non-linear load here, unbalanced non-linear load, so you have all kinds of harmonics and sequences, then zero sequence currents, third harmonic, they are trapped here, but they are not polluting the network here if you are using delta. Okay, so what is important here? If you have positive sequence current, if you on the secondary side, when you bring it to the primary side of that transformer, it will get a phase shift of minus 30 degree. And if you have a negative sequence current on the secondary side and you bring it to the primary side, IA capital, then you will have positive plus 30 degree phase shift. This is very important to know, because we know 7th harmonic is what? Positive sequence. And 5th harmonic is a negative sequence. So in the secondary side load, if it is generating 7th harmonic current, so when it will go other side, primary side of the transformer to the network, then the 7th harmonic will have phase shift of minus 30 degree. And 5th harmonic is a positive sequence. When it goes to the primary side of the transformer to the network, it will get plus 30 degree phase shift. So this is very important to know. Later on we will use this technique for harmonic cancellation. So two important effects in DY11. Positive sequence and negative sequence components rotate in opposite directions. Minus 30 for positive sequence for 7th harmonic, plus 30 degree for the negative sequence, 5th harmonic. Zero sequence current is absent in the primary line of the currents. You see, in IA, this is the primary side current which is going to the line of the primary side. There is no zero sequence currents. They get trapped by the delta connection. So in delta connection, you have the current IAB, right? It is trapped here. You see the zero sequence current is here. So it means all the zero sequence currents are trapped here. So they are not going out. If the zero sequence currents are not unbalanced, then you will have other things, right? Now, same way you can analyze DY1, which is also very popular in India also. DY11, DY1, these are popular transformers in India also. Okay, so engineers should know the characteristic of those transformers, and they have to choose which transformer is proper for your plant, what kind of harmonics are there, right? So this is just an example of DY1. And in DY1 we know the secondary side voltage is lagging behind 30 degree by the primary side voltage. This we have, that is why we have one here, right? Now if you see the line side of the current of DY1 transformer, if you have positive sequence current, then it will have plus 30 degree. It means the 7th harmonic will be shifted by plus 30 degree, while the 5th harmonic will be shifted by minus 30 degree. While in DY11 it was 0, 7th harmonic was shifted by minus 30 degree and 5th harmonic was shifted by plus 30 degree. So you have to see the difference. Okay, 7th harmonic plus 30 degree, 5th harmonic is minus 30 degree. So this is, we have seen. Now we have another transformer YD11. This is the characteristic, how the phases are shifted. YD11, it has this characteristic. Then we have delta zigzag DZ0. 0 means there is no phase shift between the secondary side voltage and the primary side voltage, right? So we don't have time to analyze. Finally, you can see there is no phase shift in secondary side voltage and the primary side voltage. You can see AB is his, AB here, phase AB here like this. There is no phase shift. But you have to see the advantages of zigzag. Advantage of zigzag we have already seen earlier. No core saturation even with half wave rectifier or DC component. So this is the advantage of zigzag connection on secondary side. If you have a zigzag connection, then your core will not be saturated. Okay, transform, because there is no third harmonic. Okay, no zero sequence current in delta. This is the way. But if you have YD11 or YD1, zero sequence currents are trapped in the delta. So although they are not going out, but they are heating up the transformer, right? So this is the disadvantage. But if you are using zigzag connection, even here you don't have the zero sequence current. Okay, and there is no phase shift if you have DZ0. So I will not go in much details of this, although I have put it in the notes. So you see, 7th harmonic, and this is the 5th harmonic. No rotation of positive or negative sequence harmonics. This is DZ10. So this is 60-degree phase shift between the secondary voltage and the primary voltage. That is, the secondary voltage is leading by 60 degrees to the primary voltage. And then you can see the rotation of positive sequence and negative sequence. Now this comes a very interesting things. Okay, so harmonic elimination, by why we were studying all this phase shift. So now is the time to apply whatever theory we have learned to see how we can use. So this is what I was talking yesterday when I was giving a speech. Okay, there is a factory plant, there is one line of production, and it is generating some harmonic 5th, 7th, but they are not polluting much to the network. So engineers and everybody is happy that it is not much pollution. Now the time comes to put this secondary line of production, and then that is the time an engineer has to see seriously whatever load, non-linear load you have, what kind of harmonics are generated by that load and how much, and they are going to the primary side and they are spreading around the internal distribution system of the plant. Although presently this is not serious, but if you put the second line or third line of production, then it becomes the serious matter. Okay, so if the engineer says, okay, first line of production we already have and it is not giving much problem, so we can buy the same equipment for the second line. So because we don't have any problem, so we put the same thing for the second line. And I told you that this is the worst decision which can an electrical engineer take. So he has to be very careful to think about this. What is the harmonic situation? So suppose we have DD0 plant here, transformer, delta in the primary, delta in the secondary, and 0 degree phase shift. Now you have non-linear load here. So 5th harmonic and 7th harmonic are generated here, which will be transferred here, I5, I7, which will go here, I5, I7 in all the three phases, A, B, C. Now you have similar transformer here, DD0, suppose we have DD0 here, and these loads are identical. It is generating I5 and I7, which is transported here, I5, I7, which will go here, this way, I5, I7. Now you have two I5 and you have two I7. See? So this is what is happening. All the harmonics are adding up because the engineer said, okay, because first line is working fine and the second line should also working fine. And I was surprised to see that 2 years ago, as I told you, one of my students, he was working as an intern in the company Rio Tinto in the north of Quebec. It was a very big plant. Each transfer was multi-megawatt MVA size transformers. And he was showing me the diagram. And he told me, Professor, you told me in the course this thing, and I see now there are 6, 7 multi-MVA transformers, and they were having phase shift with respect to each other. So this is not only for small load, even for large size load also it is very important to see what harmonics are being generated. So we know that if we have similar transformer for similar type of load, it will generate a lot of problem. So that's why we take the example of DY1 transformer. Primary is delta, secondary is star, and there is 1 means the secondary voltage is lagging behind 30 degree with respect to the primary voltage. So will it be able to cancel 5th, 7th harmonic or not? This is what we have to analyze. An engineer has to see this. So see, we have the zero connection. First transformer. This is the primary side current. Okay. Secondary side, because this is DD0, there is no phase shift, so it is in the same phase. Secondary line current, secondary side current is given by this. Now, suppose your nonlinear load is generating 5th harmonic, secondary side 5th harmonic, and this is the equation for 5th harmonic, which you transfer to the primary side. This is DD0, there is no phase shifting in the current. So they are in the same phase, 5th harmonic. Right. Now see the second transformer, DY1. This is the primary side current of the second transformer. And in the secondary side, this is one connection. The secondary side voltage is lagging behind 30 degree. So the current is lagging behind 30 degree. Okay. Now let us see the 5th harmonic. What will happen to the 5th harmonic of this second transformer DY1? Okay. So we were having minus 30 degree. Now the 5th harmonic is there. This is the phase shift. This is how much? 150 degree. 150 degree, right? Now when we bring this to the primary side, this is the secondary current. When you bring it to the primary side, so what we saw for DY1 transformer, 5th harmonic is the negative sequence. Let us go and see DY1. DY1. This is DY1. 5th harmonic is the negative sequence, minus 30 degree phase shift. So from the secondary current, 5th harmonic, when it comes to the primary side, minus 30 degree phase shift. So see, minus 30 degree phase shift. This is as it is here. And when we are coming to the primary side, we are writing minus 30 degree phase shift. So this is 150 and this is minus 150 minus 30, so minus 180 degree. Okay, so the source current from the first transformer and from the second transformer, fifth harmonic. So from the first transformer there was no phase shift, DD0 transformer, and second transformer DY1, it has minus 180 degree phase shift. So fifth harmonic is cancelled, right? So this is the advantage. Instead of using second DD0 transformer, we are using DY1 transformer, which is cancelling the fifth harmonic. Same thing you want to try for seventh harmonic, but you can try it, go to your home and try for seventh harmonic. Actually it will cancel the seventh harmonic also, but it will not cancel this 11th and 13th harmonic. It will again cancel 17th and 19th harmonic. So other harmonics are also calculated this way. So I will not go through again this thing. How much time is left? When I have to finish? But okay. Okay, but let me see. Because I have another important topic to discuss. Multipulse transformers. Yeah, this was I am supposed to teach it today. But it's okay, I will just give you the basic idea. Okay, then I will continue it tomorrow. Okay. So it's a very important topic of multi-pulse methods. Okay, just another 15 minutes and I will then continue it. Multi-pulse methods. Okay. So there are so many things, different kinds of transformers I wanted to discuss. So let us see the application of multipulse methods. There are a lot of applications here. As you can see, their application is in variable speed drive. Actually, everything is related to the power quality, and it is a very hot topic, multipulse methods. Lot of people are working, and every day new patents are coming out for multipulse methods. Okay. So application are lot of application of multipulse method, like in variable speed drives, HVDC, chemical industry, electroplating, battery chargers, uninterrupted power supply, high power induction heating, converters for aviation industry. See, everywhere nowadays multipulse techniques are used. These are known as rectifiers, fed by three-phase source. So if you are having rectifiers, there are some power quality problems. On AC side, voltage and current harmonics are generated, poor power factor. We already have the idea of rectifiers, right? And on DC side, you have the voltage ripples. If the rectifier was already installed, many methods are available to improve power quality, like you can put passive filter, active filter, hybrid filters, right? But in certain cases, the capacity of these filters become the same as rectifier capacity. Okay, it causes the following problem: increases the cost, because now you have some problem, you find the solution, and the solution is costing the same as the original equipment, right? So increase in cost, increase in losses, increase in number of components, causing the decrease in system reliability, because you are putting another equipment with lot of components. So reliability goes down. Therefore, for new installation, it is preferred to modify the total concept. The technique is called passive wave shaping. And what is the advantage? Simplicity and economic. Passive wave shaping is based on magnetics in three-phase AC system. Therefore, together the system is called multi-phase multiplication. There's a lot of development going on in this area. Recently, many articles, even few years back, we wrote a very big review paper on multipulse technique with Professor Bhim Singh, me, and we people wrote a very, and you will find so many articles and so many multipulse techniques. Two major advantages of multipulse system: decrease in current harmonics on AC side, decrease in voltage ripples on DC side. See, this is the example which we have already seen. See, this is DY1 transformer and this is DD0 transformer. Just now we discussed this thing, right? So you have identical equal loads here on the side, and this is the transformer DY1 and this is DD0 transformer. So if you write the equation of current here, this current is proportional to the fundamental 5th harmonic, 7th harmonic, 11th harmonic, and if you write I2, it is proportional to these things, but see the sign. So if you take the sum of these, this will cancel out, this will cancel out, and 11th harmonic is added. Similarly, 13th harmonic as it. So it means that is not helping in 11th and 13th harmonic, but again on 17th and 19th harmonic it is cancelling. Now the problem is that sometimes load may not be equal. So what is done? You have a single load supplied by DY1 and this is DD0. So this is what, this is diode bridge rectifier, this is diode bridge rectifier, and this is the same load, but you see there is a phase shifting. Here 30-degree shifting, here is no shifting. So basically the voltages coming here. So see 30-degree phase shift between the two voltages. So the ripples will be generated here on this side, which has the instantaneous 30-degree phase shift. So voltages are not equal, so there may be some circulating current problem. So that's why we use interphasing transformer to smooth out the operation. If the converters connected in series, there are certain advantages. You don't need interphasing transformer if the converters are connected in series and you have higher voltage available. What are the disadvantages? Reduced loss current, increase in losses. If the converters are connected in parallel, advantage is increased load current. Disadvantage, you need interphasing transformer and you had, for parallel, you have lower voltage. In general, now in DD0, DY1, we saw 30-degree phase shift, which is helping in cancelling the harmonics. In general, the minimum phase shift required for cancellation of current harmonics in converters with 6 pulse waveform, this is 60-degree divided by number of 6 pulse converters. Like for example, in our DD1 and DD0, we used 2 converters, 2 6-pulse converters. So if we are using 2 6-pulse converter, which is giving you 12 pulses, right? 6 multiplied by 2, that is 12. So you will have, here you have 60 divided by 2, it means you need 30-degree phase shift, and this is what we gave, 30-degree phase shift. In DD1 and DY1 and DD0, we gave 30-degree phase shift, multiplied 12 pulses, 360 degree. If you have 3 converters, 6 pulse converters, then 60 divided by 3, which will give you 20 degree phase shift. So if you have 3 6 pulse converter, you need minimum 20 degree. You can have more, but minimum you need 20 degree phase shift. And 3 6 pulse converter, it means 18 pulses, right? So 18 multiplied by 360 degree. If you have 4 converters, 24 pulses, then 4 here, it will give you 15 degree phase shift multiplied by 24 pulses, 360. If you have 5, then 12, so divide by 5, 12 degree. So this is how you can, if you have 6, then 10 degree phase shift and 36 pulses. So this is how you decide what is your objective, right? So if you are having one converter of 6 pulses, then this is the formula that what harmonics it will generate. It will generate k equal to 1, so 5th, 7th, 11th, 13th, 17, 19, those harmonics are generated with one converter of 6 pulses. If you are having m converters of 6 pulses, so this equation can be written like this, and amplitude is this. So if you have, it means if you have 3 converters, so for k is equal to 1, 6 multiplied by 3, so 18k plus minus. So if k is equal to 1, see, you have minimum 17th harmonic. 3 6 pulse converter means 18 pulses. In 18 pulses, minimum you will have 17th, 19th, and then 35 and 37th. See, this is a big advantage. If you are using 3 converters, 6 pulse converters, you are having 18 pulses. But you will have 60 divided by 3, 20 degree phase shift. So between the 3 converter, you should have 20 degree phase shift to get this advantage that so many harmonics are removed of this amplitude. Okay. So, okay, I think I should stop here for today, and we will continue with this tomorrow. It's okay? Yeah. Okay, sir. Thank you.